In my previous video, I talked to you about the various trajectories a craft can follow when it goes by a planet or any other mass, actually, for that matter. In space, in our solar system, we got the sun at the center, the sun, and multiple planets here and there. And the thing is, this could kind of distort what we're looking at, because when we have a planet and the sun as such, the planet's got its own sphere of influence. But this picture is wrong. Ideally, a mass sphere of influence extends all the way to infinity. It extends in all directions, completely to infinity. But because of the presence of other masses, we're restricting the sphere of influence to a planet or any other body in space to a particular circle or a sphere or particular radius. And when the body is not in the sphere of influence, we consider it in the sphere of influence of the larger mass, that is the sun in this case. So it's under that chain sphere of influence of the sun, which controls the whole solar system. I'll now talk to you about the case where I've got just one body and the spacecraft. While I told you that this spacecraft could follow a circular, an elliptical, a parabolic, or a hyperbolic trajectory across this body, I could have been just lying, because who's gonna really go to space and check what kind of trajectory it's gonna follow? So I'll prove to you in this video that the trajectory the spacecraft follows is one of these conic sections. To do this, I'll just assume a few things. I will try to calculate the energy of the orbit, and I'll show you that it's related to the eccentricity, and rather it's proportional to the eccentricity, like this, and show to you that the various for the various cases of energy, we've got various eccentricities. This derivation isn't one of the loveliest derivations in the world, so what I'll be doing is I'll link this derivation in the description, and you can check that out if you're interested. It's really algebraic and kind of long, but I'll take you from here. This is the total energy. This total energy has two components. One is the kinetic energy, and the other is the potential energy. This potential energy equals minus G into capital M into small m by R. I've forgotten to mention these. So this is small m, this is capital M, G is the universal gravitational constant, and this distance, this will be the center of mass of this object, so this distance will be R. Our kinetic energy in the meanwhile will depend upon this spacecraft's radial velocity and angular velocity, and it will just be half m into v square, just v square, and where v depends on both of these. So this equals k into e square minus 1. I'll define a mu equal to small m into capital M by small m plus capital M. So what this essentially does is, well, here we've got two bodies. What mu does is it makes this two body problem into a single body problem. I'll also define this other constant R naught. This R naught equals L square by mu G small m capital M. G is the gravitational constant, this mu is this value, and L is the angular momentum which this M possesses. I'll just give it a path. So this path could be any shape. L is the angular momentum which this body possesses. So R naught, this is actually called the semi-lattice rectum. Semi-lattice rectum. And this value is L square by mu G small m into capital M. The orbital equation of this body would be r equals r naught by 1 minus e cos theta, and this e happens to be our eccentricity. From this equation and the derivation that I've linked below, it can be shown that the eccentricity is equal to the whole root of 1 plus 2e L square, E is the energy, L is the angular momentum, divided by mu, I've got mu in the top left corner, into g small m capital M whole square. So this is our eccentricity. Now what I'll do is I'll take out this expression and I'll rearrange it. What I'll get is r equals r naught plus er cos theta, and this is actually the general equation of a conic section in a different way. This is when we've got polar coordinates. So I'll make these substitutions. X equals r cos theta and y equals r sin theta. So x square plus y square is equal to r square cos square theta plus r square sin square theta. So x square plus y square equals r square basically, because cos square theta plus sin square theta equals 1. So this can be rewritten as whole under root of x square plus y square equals r naught plus ex, because this part's just x. Now what I'll do is I'll just square this and rearrange this. So x square plus y square equals r naught square plus e square x square plus 2 e r naught x, and I'll just put this over there. Basically I just bring all the x terms on this side. So x square into 1 minus e square minus 2 e r naught x plus y square equals r naught square. So in my general equation for a conic section video, I have shown you an equation that's similar to this, but this is a special case of an equation. This is when the axis of a conic section happens to be the x-axis. So if this were the coordinate axis, then a conic section would have an axis that's the x-axis, that is the major axis. Here, if this is the case of an ellipse, this is the case of a parabola. For a circle it doesn't matter, and for a hyperbola it'd be something like this. So the major axis basically, or it's got different names for different conic sections. So the more important axis of the conic section is the x-axis in this case. For all the cases that I'm going to consider after this, I'm going to take angular momentum L not equal to 0 to just basically say that a body is moving. For my case 1, I'll substitute the eccentricity equal to 0, and our energy is at its minimum. So E is E minimum, and this value is less than 0 because our eccentricity is 0. If we substitute this in that energy equation, the total energy equation that we got, this would be the least possible energy case. So when E is E min and the energy turns out to be negative, because potential energy U is defined as minus gmm by r, so it's negative, I would get this equation, this familiar equation, x square plus y square equals r naught square. And tada, this is the circle equation. So the first case which I told you, the case of kind of similar to the moon's orbit in my previous video, that is, so this is proof for the existence of that circle, or that very close to circle shape. Now I'll take case 2. Case 2 is when I put my eccentricity between 0 and 1. And in this case, E minimum, not the E minimum, now our energy is sandwiched between E minimum and 0. Total energy. So now we've got a little more energy than the minimum case, but it's still less than 0. If I do this, I'll get this equation, y square and something multiplied to x square. I'll just call that k1 x square minus k2x equals k3. So we got three constants over here. I'll tidy this a bit. So y square plus k1 x square, this could just as well be 2k2 dash, so minus 2k2 dash x, and we just divide this whole thing by k1 by k1 by k1 equals k3 by k1. From this k3 by k1 I would just add k2 dash by k1 whole square on both sides plus k2 dash by k1 square. So this is a square that goes off. So this is a square. So we've got y square by k1 plus x minus k2 dash by k1 whole square equals, I'll just call this some other constant. I'll call this k4. And I'll just bring this k4 down here, y square by k1 k4 plus I'll call this constant k5. We got a lot of constants over here. X minus k5 whole square by k4 equals 1. Tidying the whole thing up a bit, I could just make this y square by b square plus x square by a square equals 1. This is a slight anomaly because I've considered the ideal case where the center of my ellipse lies at the origin, but over here the center of the ellipse is slightly pushed away, which is why we got this extra constant over here, but we can still show that this is an ellipse. So this case is the ellipse case. I'll cut all of this out. So this is the ellipse case. I'll take case 3 where my eccentricity equals 1. So over here my energy equals 0 because I've got an a square minus 1. If I just put 1 over there, I get 0 and boom, the whole thing becomes 0. But here I'd like to tell you one more thing. Kinetic energy equal to the potential energy because E is equal to k plus u and k has to be equal to u so that they cancel. U is negative, so addition of them would cancel. So k has to be equal to u, or rather the magnitude of k, the modulus of k has to be equal to the modulus of u. That'd be a better way to put it in, right? Modulus of k equal to modulus of u. So over here the addition of both of them would cancel each other and give me 0. So for this case I've got y square minus 2 r naught x equals r naught square. No x square term over here, so this would be y square equals x square, no need x square, equals r naught square minus 2 r naught x. I thought plus, so I thought I'd just get an x square and complete the square, but that would just get us nowhere. That's pointless. So again rewrite this as y square equals x plus k into k dash. So this is a parabola equation. I showed you a very similar equation, y square equals 4x. So again the center of the parabola is shifted off, so we've got this anomaly over here, but either way this can be equated to something similar to that. Actually for this equation as well, what I'd like to do is I would make this a capital X, the shifted x square. So here what I can do is I'll make this y square is equal to 4a capital X. So that's the shifted x square. So now I'll just clear all of these. And this is the parabola case, case 4. E, the eccentricity is greater than 1. Now our energy would be greater than 0 as well for the first time. And this, for this, what we'll have to do is I'll just call this minus kx square plus y square minus k1x square rather minus k2x is equal to k3. Again, I just had to do the same thing which I did for the ellipse as well. So and dividing everything by k1, k1 off, k1 off, k1 off, k1 off, and just multiply. Oh, I forgot the 2 over here, so there's a 2. So again, I just had to take the square, and in the end what I'll get, I just skip to the finish. Y square minus b square is equal to x square minus a square is equal to 1. This is what I get in the end. If you want, you can just do the simplification for yourself to see what to check what I'm saying. But no, I shouldn't be saying x, I should be saying capital X again, because we gotta shift it center. And clearing this, and clearing this. So here they are. We've got 4 conic sections: circle, ellipse, parabola, and hyperbola. And we've shown you how I've got them from the equation of the trajectory, the general equation of the trajectory, and from the energy derivations. I have shown you that they're circle, ellipse, parabola, and hyperbola respectively. I'd like to go a little bit further. Over here, if you notice, we got the energy, basically this part. The energy is less than 0. So, and over here as well, we got the energy is less than 0. So, whenever we got the energy less than 0, the tiny body is forced to go around a bound path around the bigger body. So now we've got this bigger body. Whenever the energy is less than 0, that is the magnitude of kinetic energy, the absolute value of the kinetic energy happens to be less than the absolute value of the potential energy. This means the body is trapped and it's forced to orbit the bigger body. And over here I've got E is 0 or E greater than 0. So whenever my energy is greater than or equal to 0, I've got this case where the potential energy, the magnitude rather, is less than the kinetic energy, or less than it equal to the kinetic energy, magnitude of the kinetic energy. Then the body, the tiny body, goes in an unbound path. It just escapes. So now if the tiny body entered like that, it would just follow that path and it would go away. It doesn't stay around hang out around the bigger body. And this comes from the fact that the parabola and the hyperbola are open curves from the graphs, and the ellipse and the circle are closed curves from the graph. As a result, depending on the energy, the spacecraft either stays around bound or goes away, escapes. Do check out the link in the description for the whole derivation, the proper derivation of the energy, and also for some extra bits and stuff on gravitational trajectories.